Good morning, everyone. Welcome to join my session online. My name's Ricky-san. So today I will be presenting performance-oriented design of scalable graphs database. I understand this is a very gigantic topic, and there are just a lot of things we need to cover, and it's impossible to cover everything from all aspects in just 1/2 hour. So today we are sharing our experience based on our, projects over the past couple of years, working in real world application scenarios that how a really scalable distributed graph database can handle, high performance scenarios. The findings, the comparisons versus traditional database design. A lot of things are quite different, but a lot of things can be learned from our past mistakes or practice. Uh, the presentation, I mean, the content was prepared by me and my colleague Jamie. Jamie is not with me today, so I will be do the presentation by myself. Without further ado, I'm going to start it. So let me introduce a concept to the audience here. Like, this is really about the convergence. I mean, this is a major trend happening as we are, working in industry or in the academics. This major converging trend is really infrastructure converging of AI and big data. So over the past 40 years, uh, allow me to, okay, all right. So over the past 40 years, we're seeing that AI going from, expert system back in the 80s, 90s to machine learning and to deep learning and to today's OpenAI and ChatGPT. So that, that's the things that we have been seeing AI going that way. And on the right-hand side, we see, we're go over the past 40 years, we have seen things going, the infrastructure, the data processing technologies going from relational database to big data to fast data. And then what's next? And what do we see, in AI and big data? On the left-hand side, we do see, there are a lot of black box stuff. Black box means low trust to human beings, low trust to human decision makers. We need to understand what exactly has happened. Why the AI, AI algorithm or program or system or product reached some, decision conclusion. Are we clearly confident? Are we clearly, uh, know what's going on? I mean, so that means the low trust, the black box has been the major problems. And on the right hand side, we see big data. Over the past 10 years, 10, maybe 15 years, with the rise of cloud computing and big data, we have seen a lot of infrastructures, highly expensive, not that very fast, with high maintenance, uh, very slow, storage and computing, low performance. So what do we want? What we are seeing and what we want is the converging of the infrastructure. And we need a couple more things, like explainable AI, augmented intelligence, real time, and deep data processing, data analytics capabilities. So to summarize, we need transparency. We need to gain human trust in the AI systems, and we need fast and deep BI capable, data processing capabilities. Ideally, even with smaller footprint, from ESD and carbon neutralization perspectives. So what kind of technology from the infrastructure layer potentially can provide these promises? Graph, and we're calling this graph augmented XAI. So essentially, what is graph? I think we still deserve, to maybe use 1 to 2 slides to give a quick introduction in case some folks are not totally familiar with the graph augmented intelligence, this concept. So essentially, graph augmented intelligence is a form of artificial intelligence, and it's really ideal technology or infrastructure for smart enterprise. Also, we believe if we are building a graph database management system, it should be a computing first. Well, this is the part very different from other or traditional database management systems. So computing first. Previously, we were only focusing on storage. Everything is storage first. Once the data is persistent on storage layer, a lot of people don't really care about the computing part. But in the graph era, in graph database, we do need to pay a lot of attention to computing efficiencies, et cetera, et cetera. Essentially, graph database is also a high dimensional high dimensional system with the equivalent data modeling capabilities. Well, what's illustrated here, like in the traditional tables, we have a lot of siloed, sometimes may not be siloed, but it's not naturally intuitively connected data, in different tables or different databases. Graph connect all of them together, right? So there got to be some pathway to transforming from relational database to graph database, because the relational database are not, that flexible. It's sometimes even counterintuitive. And in terms of the capabilities to deeply penetrate data, connect data, correlate data, it's slow, it's shallow, and we all talk about the Cartesian product. We understand, the relational data model comes with high computing complexity. On the other hand, the graph database is supposedly should be more flexible, intuitive, fast, deep, with great explainability, white box. And also the computing, when we are doing computing analytics or query, the graph database should come with much lower complexity, right? So from the real world industry scenarios and perspective, we should say that what exactly is a smart enterprise? Smart enterprise, they should adopt certain level of data intelligence, and also adopt, infrastructure revolution. And what's the largest, common factor? That's graph augmented intelligence from our, based on our study understanding. So again, we probably need, this is the second slide, explaining the very basic stuff in traditional, in relational database. Even if you are trying to do something like, trying to figure out employees belong to multiple departments, in relational database, you're gonna need a lot of join, lookup stuff. And in a truly native graph setup, it's really just doing a very simple one hop traversal. Starting from that person, assume that person is called Ricky, and Ricky belongs to multiple departments. It's just one hop, or multiple, triplets. Person belongs to department. That's it. Super intuitive, super straightforward. So how exactly, assuming you have a lot of data in the relational tables, right? How are you going to migrate? How are you going to migrate from relational database to graph database? Well, I guess the key thing here, what I'm trying to say is there are more than one ways to migrate data. What's being shown here is actually, we're showing two models, simple graph versus multiple graph. Uh, and as you can see, well, we'll get to, their differences are pretty, straightforward. As you can see, in simple graph setup, there are more types of entities and even relationships. And in multigraph, so we got fewer types of entities and even like types of edges. Simply because why we're seeing this difference is that simply because I probably should go to this slide first. Let's look at a simple graph versus multiple graph. I'm gonna give you uh, you know a real use case, assuming in between a pair of accounts there are say 1,000 transactions between them. If we are using the simple graph data modeling mechanism, there will be 1,002 nodes plus 2,000 edges. And in multiple graph setup, we need only 2 nodes and 1,000 edges. That's where the definition of multiple graph, multi-graph come from, right? In terms of storage, roughly, simple graph is 3 times more expensive in our case, right? The computing could be more challenging for simple graph, right? Because if you are trying to traverse from A to B, or assuming that's only 1 hop, if you're going really 3 hop, A to B to C to D, well, when I say B, C, D, uh, in the real world setup, a densely populated data site, you're gonna see that doing things in a simple graph way means exponentially more challenging. Meaning you're gonna traverse, more nodes and edges. So the computing complexity is actually naturally higher, exponentially higher. And also, on the other hand, multiple graph is more natural to human beings in terms of data modeling, right? If you have multiple transactions, use edge to present as a transaction, right? And naturally, transactions to edge. But in simple graph, as you can see, transactions are all modeled as entities, which is quite counterintuitive. Uh, Given the time restriction, we're not able to expand fully on this topic. But what my point is that uh, multiple graph is more natural and it's backward. It can be backward compatible with simple graph, but it's going to be very difficult for simple graph to model as a real world, intuitive, natural multi-graph. And sometimes the complexity, involved is actually higher with simple graph. But in many real world applications, especially like in fraud detection, simple graph is still very useful. So let's go back to the left-hand side. As we can see, like essentially most of the things, most of the traversals we talk about with graph database really from, like BFS, DFS. These are the 2 major types. But forget about it. Throughout this deck, we're not talking about that. Uh, a lot of the problems can be solved with graph, like, behavior analysis. UBO, ultimate beneficial ownership identification, risk penetration, quantification, even like liquidity risk, treasury management, asset liability management problems can be better solved using graph technologies. Uh, Way more efficient than, for instance, like the traditional, relation database based or data warehouse based technologies. And also smart marketing, intelligent prediction with more accuracy. A lot of things can be done. So in real world, a lot of algorithm or traversal are not exactly BFS or DFS. It could be a combination of both. It really depends on the requirements. So we probably should talk about query language. Let's jump to that here. So assuming we have a very, simple, this can be seen as a triplet because that's from, starting from a person uh, whose job is a chef, right? That's a typical, in RDF, you would call it's a triplet, right? By using Cipher, Cipher use a lot of labels, which is considered a special kind of index, right? Acceleration mechanism. Uh, so that's how you're going to present this triplet, right? And this is how GCCO, Tiger Graph would present. You need to create that kind of query. My God, that's pretty complicated. Also, in Ultipa query language, that's our product. So there are actually two ways to do that. One is a schematic, the other one is schema free. As you can see, so I'm going to go a little bit that the triplet is really node, edge, node, right? Very straightforward, except that we're using schemas, right? The person has name, relationship, that's a job, job is, and so if it's a schema free, there's no need to use any schema. We pretty much go freestyle. So both are, I would say it's quite intuitive. We're calling this demi schema because we give you the freedom, but if you want to go very strict with data types, you can go schematic, right? All right, so this is Gremlin, right? Gremlin, I always find it's a pretty challenging to use Gremlin. Uh, well, in short, some query language can be very complicated. Some can be even confusing. So it's your pick. In terms of how you're going to optimize things, that's going to, the complexity of your language, the counterintuitiveness is going to affect, counter effect the way or to the degree of optimization you can potentially do to optimize your, scalable system design. So generally speaking, what kind of a product matrix we're talking about when we are building a real world, enterprise grade graph database? You probably want something. We're calling this seamless union of graph computing and two chains, right? So the graph engines has multiple components. The compute engine, the graph native. We're talking about native storage engine, compute engine, query engine. Essentially, all of these are on the left-hand side are graph engine. And on the right-hand side, on the two-chain side, you're going to have, visualization, explainability. We're calling this XAI. So combined, it's graph augmented XAI. It's very much like, what's illustrated in that book, the Thinking Fast and Slow. It's like, the right brain or the left brain combined to form, this is very much like system one, system two combined, forming an enterprise ready real world graph database. That's the kind of things that you need. All right. So let's get into our topic for today. The real topic for today, the evolutional path from single instance. You just have one standalone, instance doing everything concerning graph database to reach a stage where you have a pretty much endlessly, scalable system. In between, there are quite a few steps in terms of, the evolution from standalone to master slave. Some people call this, HA mode, or which is even compatible with disaster recovery mode, right? And also you have raft. Raft is a very rudimentary type of, supporting cluster that's distributed, that's allowing distributed consensus to be performed across multiple instances within the cluster. And more advanced form of that is HTAP, meaning, within the same cluster, you have a certain functionalities, that can be taken care of by certain instances, different, instances jointly performing TP and AP in a hybrid mixed way. That means within the cluster, you have the capacity to really, intelligently picking the right instances to handle the right workload. So that's clearly something more advanced, more sophisticated than the master slave mode. On the other hand, in a distributed consensus system setup, the data consistency is pretty good. Is way better than the other models. to go a little bit forward from HTTP mode to proxy mode, this is, I would call both proxy and federation mode. Occasionally people call this map reduced, So it's by divide and conquer, dividing the data set onto multiple instances using a proxy server. Sometimes we also call this name server to distribute, the workload. We'll get to that in details later. And also, federation is considered a more advanced form of proxy. Of course, if you would like to go the extra mile, traveling to sharding, like we also introduced like meta server and working with name server and shard server, and you have really sophisticated, partitioning mechanism, meaning you're going to have to cut logically, the one graph data, gigantic graph data set into multiple partitions, and you're working genuinely in a sharded environment. That's the most sophisticated form, of distributed graph systems. But what a lot of people don't want to talk about is the performance. If you are sharding, if you use sharding, you're partitioning, and we're talking about graph queries, because graph queries really potentially traverse the entire data set or a certain portion that's unpredictable. How are you going to ensure the performance drop? There will be a performance drop. This is for sure. Don't deny it, right? And how are you going to make sure the design, the optimization can alleviate the problem, not exponential drop? Sometimes the performance drop can be 100 times, even like unbearably slow. So that's what we're going to talk about for the remaining of this presentation, right? So, okay, I'm going to introduce three types of architectures throughout this presentation. The most basic one is called Ultipa HTAP architecture. This architecture has been deployed with quite a few, GC. Folks, GC stands for globally systemically important banks, meaning large banks, large retail and commercial banks, and also stock exchanges and insurance companies. What I'm saying is that these are very serious users, enterprise users. So they care about their data consistency, they care about performance, they care about how robust your overall architecture is. Uh, if it's not robust enough, it's not mature enough, it's not fast enough, you're not going to get a deal, right? So this is the whole picture. I'm uh, so we talk about there are multiple engines. Now, these are the engines like the persistent layer, the compute engine layer, also the query layer. The key thing is, as you can see, there are multiple HTAP instances, right? And this is a logical architecture. Normally, the minimum cluster setup is with 3 instances. We're calling this, they're forming a CAP, the impossible CAP cluster. Now, this is the very basic setup using only 3 instances. So the key things are illustrated here. From bottom to up, we can see that distributed consensus is the very basic to make sure the data is consistent.
Hi, hi, Ricky. I think you are muted. We can't. We are not able to hear you at all.
Okay, so guys, are you able to hear me? Okay, okay, all right. So I guess we uh, I have no idea, over like the past 20 minutes, I was on mute. There could be something wrong with my browser. Okay, so let me just continue from where I left over, right? So now this is the large scale grid architecture we talk about, right? Different. Let me probably I should go back one more slide. Uh, Back to the HTAP architecture, right? Uh, like I said that we have, the cap cluster, which essentially is distributed consensus forming between, multiple instances. For instance, like three instances, and there is like multi-tier storage acceleration and parallel high density parallel graph computing. Essentially, to allow data to quickly go through, the system and to be processed and to return things. A lot of these, analytics can be done in real time. So that's the uniqueness of HTAP architecture. Uh, and and large scale grid architecture is different in that we introduced, like name server and meta server in a, map reduced fashion, but we still preserve some kind of characteristics from the HTTP architecture, and that's the Ultipa server clusters. We can also call these HTAP clusters. Each cluster, for instance, there are three nodes, three worker nodes. They each have storage and compute capacities. A lot of processing can be done, locally within that cluster. But of course, the name server will be functioning like, a map reducer, distributing workloads to different clusters. A lot of things also, minimum traffic will be aggregated, uh, will be actually processed uh, over each cluster and merge back to the name server. But overall, name server does not handle major, the large does not handle the large share of the data processing, right? So name server's workload is not that high anymore. This is very much unlike the Hadoop, the MapReduce, classic MapReduce case. So there are some kind of a acceleration mechanism. But the tricky thing is that it's up to the DBA, the graph database admin, to decide how we're gonna, partition the data based on what kind of logic. I hope, hopefully I'll get time to talk about that when we talk about the next, the the pure, genuine shard architecture, so that we know the difference. Essentially, there are 2 points. One is the high performance HTTP clusters, which can be geo-distributed, right? And also how the cluster, the scalable cluster can be still managed effectively using the name server and the meta server. So this is the shard architecture, right? The tricky part with the shard architecture clearly is we still have the name server, meta server, shard server, but things are just so much more complicated because we have done lots of cutting, like a bit edge centric cutting or vertex centric cutting, but still major optimizations can be done. For instance, like it's still compute centric storage format, like from shard 1 to shard n, essentially in the sharding server clusters. And also for name server, deeper query optimizations can be done. So we'll talk about that later. What's showing here is that when you're designing or using a graph database, there are a lot of visual things that you must, visual tasks you must do. Like sometimes sometimes you even need to use the WebGL to be able to help with the front end visualization, acceleration of the visualization, right? It got to be fast, it got to be intuitive, and it's actually even adaptive to your needs. The screenshot here is actually how we work by using the graph, the front end DBMS system to work with our data set, to integrate with our graph database. As you can see, this is quite peculiar with the graph database, is there are heterogeneous types of data, right? You have like nodes, which can be presented as a list, very much like traditional database, but you are also having path, subgraph, networks of data, right? And also, as you can see here, this is the very interesting part, right? This is exactly the HTTP cluster we talk about, right? As you can see, there are 3 instances, they're set up, which one you are running on, that kind of things, right? So let's continue to talk about in a distributed graph database setup, the 3 major things: the name server, the meta server, and also the shard servers or the HTTP servers. So the major main functionalities that name server has to handle, including, for instance, like RPC request. Of course, the name server need to take care of the abstract syntax tree, right, for the query breakdown. Also, execution plan optimization, right, and even including the event management, how you're going to distribute in the MapReduce mode, distribute to shard, and how you aggregate data, right? And also the load balancing of name server can be achieved. Normally, the name server is a like multiple instance small cluster. Also, a lot of hard beatings between name server, meta server, also the shard servers. Uh, and the shard and replica status will be updated also through the name server. A lot of overall, if we see this big horizontally scalable graph system uh, as a logically united one, a lot of synchronizations and cluster-wide data exchanges happen through the name server, right? And the shard server is the second major component, like the dataset management, schema management, property management, index management, and also rows, access privileges. Those things need to be taken care of by the meta server and cluster. Like the meta server tend to ask the shard leaders to report, the health status of replicas. And sharding and elasticity is the other thing that meta server handles. In some designs, uh, the entire functionalities of meta server can be consolidated into the name server, but we are separating them, just like the microservice setup. So we have different functionalities, and potentially, if you can decoupling that, uh, a lot of parallelizations can be built into the systems, meaning gaining better horizontally, scalability, right? Uh, Also, the most important factor we never forget is the distributed consensus. Consider this is an augmented, strengthened, form of raft. So let's talk about the shard server here. While shard server contains, the raw data, like the real data, the metadata, like the graph storage, there are many ways to implement graph storage. Some people prefer to use, for instance, tradition like the row-based, column-based, or KV-based. It can be even like graph-based in the so-called native graph storage way, and also computing. So why we're talking about computing? Because we need acceleration. We need a lot of things to be accelerated. You can't just imagine all things can be conducted on the persistent layer, on the storage layer. You need that kind of acceleration mechanism. But by saying acceleration, I'm not talking about moving everything into memory, which is probably not enough, and also not very uh, productive sometimes. Uh, but there are quite a few, techniques that we probably have used all of these. Vector computing in terms of from the data structure perspective. Also, you need some kind of in-memory acceleration mechanism, and you can potentially even use GPU for acceleration. Uh, and there are other techniques. I wouldn't be able to, include all of those here. Also, um, the shard server maintained heartbeat, especially the leader node, of every shard cluster, maintain heartbeat between name server and meta server to report their, replica status. So let's summarize. For distributed graph computing models, there are actually two major schools: Model 1, Model 2. Model 1 essentially, even if it's a distributed, it's still centralized. Why? Because a lot of data are migrated and aggregated to one server, like the name server, right? So the other model is the, I would call this elastic and the distributed model. Well, the purpose here is to minimize the data migration, right? At least you want delay the data migration as much as possible, and also to minimize the data migration, right? Of course, all the entire HTAP distributed consensus thing was invented to take care of that, to minimize the data migration as much as possible. The key characteristics here is about each instance must be capable of local data processing, right? Well, this is the key thing. That means if you are able to do the local data processing, that means even without data migration, you still are able to do something locally. That means you have the graph data adjacent the neighbor data within your control, readily available for computing and process, right? And of course, name server is still useful. That means for the eventual merging ranking, which happens on top of the name server. So let's use a very simple graph queries like here, what's illustrated here, finding all the nodes, assuming node has attribute called age, like this could be a person or something, age as nodes, finding all the nodes with age over 20, return these nodes, and we want to order by the node's age, the age attribute. Or it could be limit 1,000 or 10,000, whatever, how many you want, or it could be even unlimited. So from the abstract syntax tree perspective, you have find nodes, return order by limit 1. Those are the key points, right? The key components. So from the HTAP logical plan, it's a 4-step thing. Find nodes, do the order by, limit, and return, right? So in a fully distributed setup, it will be separated into 2 major components. One is called shard plan, the other one is called name server plan, right? So things happening on shard servers are really finding nodes, whatever available nodes by using indexes, right? And you can do order by, you can do limit, right? And on the name server, it's really order by merge, limit, and return. So this is the difference, or the the overall execution plan for shard servers like logical and physical plan. Now let's talk about the computational path, assuming you are doing things like trying to find path. We're calling this AB path from point A to point B, or point B to point A. It doesn't matter, right? So you need to search for node A and search for node B and calculate all the path or some path, in between these 2 entities. So how are you gonna, generate the path? How are you gonna do that? Let's take a look. So we're calling this triangular model. This, for instance, one way to do this, or 2 ways to do this, is to search node B first, then migrate data to the instance containing, a running searching for node A, then migrating data again to somewhere else to calculate the AB path. Or of course, you can go from A to B, then there will be another instance working on or calculating the eventual AB path. So we're calling this, when you are migrating from the right-hand side node B to left-hand side node A, it's called left plan, right? From the shard server handling node B, search for node B, to the shard server handling, both the search for node A and also the eventual calculation for the AB path. On the other hand, that's the right plan, left and right. That's how we do query optimization, or not necessarily optimization. I mean, that's how we do things today, right? Then how are we gonna like optimize this with like always from the cost perspective, right? So we know there are migrational costs once you are shifting data or migrating data from one shard server to another shard server, or even to the name server, right? Like what's illustrated here. So all of these path, the green path involves migrational cost, right? It doesn't really matter where exactly uh, the eventual calculation, or I mean the query data processing will happen. Uh, the key difference here is which one has lower cost and better performance. So for computational path, for all the path queries, which is unique to the name server, I mean, unique to the graph database, is to calculating the minimum cost of an execution plan. Well, this is very much like to find the weighted shortest path problem, but we are doing this across a large distributed clusters with many instances or work nodes, and how you can containerize the logical plan to the storage and to the computing node with minimum cost. So using a migrational data to trigger more pull-up calculation rules potentially can provide more opportunities for concurrency. I mean, concurrency is the key uh, to allow for better performance in terms of latency. So what's introduced here is a horizontal. It's called horizontal elasticity, but it's different from traditional database query optimization techniques that we are using. Not only horizontal elasticity, but also using hierarchical, right? So there are the key characteristics here, including sideway information passing. For instance, here from Z to W, from X to Y. And the direction of data flow is always from, you know, small data to the instance of bigger data, right? Always, because from the cost perspective, you want to do that wisely, right? And also the layered operations, as illustrated here, right? So instances without specific data flow direction will be considered as a elastic, temporary, or even caching node, which I'm going to get to in the next couple of slides. Well, what's illustrated here is that going, from the very bottom of the two shard instances, things will go up, but there are also sideway information passing for better concurrency, for better, scalability, or computing, parallel computing across multiple nodes. So how we do horizontal elasticity, for instance, like, the assuming we're doing this, like search for node B, on one shard server, and there's a potential like data scanning for uh, A/B path, right? If no optimization is done, right, there could be a lot of data exchanges in between the shard servers simply to calculate their path. But there are explicit optimizations that can be done to avoid much data scanning. So here, this is like how we do elastic compute graph. What's introduced here are actually presented here are actually four nodes, right? Shard server for searching node A, and also the search for node B happens on another shard server, and there's a next server. Uh, so these could be things that just happened based on uh, whatever retrieved from the two known shard servers. There will be two more instances. Two more, it's two plus servers. Like this is the elastic, could be just the intermediate or temporary servers uh, used for extra resources, used for calculating all the path between A and B, and eventually merging that path and go on to the next phase, right? So elastic compute nodes can be used to provide extra resources like CPU, memory. These are the critical resources but elastic computing, that's what exactly the compute nodes can offer. And also each outputs to a target oriented, in-memory computing format for accelerated performance, there would be like back pressure to the next plane or to downstream. But if eventually, the key thing here is to avoid all to all, very much like the cross-join, the Cartesian product. This is to avoid that kind of all to all exchange. That's the key thing. Another important topic to mention is the runtime statistics and estimation. There are layered approaches to this, from very simple, very rudimentary ones to very sophisticated ones. For instance, what's illustrated here is this. It's very much like 5-layered approach, right? The most basic first layer is to evaluate, for instance, like the property of the graph, like how many schema you have, labels, properties, nodes and edges, very basic ones. But it could be difficult to really understand how many nodes are isolated there, how many supernodes are there. But we should be able to know that, because when the data is ingested into the graph database, right? So it was really ingested node by node, edge by edge. So we should have that kind of a basic knowledge. How many nodes are isolated? How many edges are connecting to each node, right? So that we should know from the statistical data point of view how many supernodes if you draw a threshold or bar. And the second layer of estimation is, are you able to tell the density of the graph, right? Which part are particularly density populated, which part are not. So this is advanced, slightly advanced features you potentially can generate out of estimation. Well, there's another category of estimation that you can potentially do is the maximum. For instance, maximum or average or minimum, the traversal cost range of the graph. When you are running a graph query or graph algorithm, are you able to tell the range potentially to estimate the high bar and low bar in between? Well, we know that to completely understand a graph, that's an NP hard problem, and that's going to be very costly. We're not talking about that. We're talking about by doing sampling, some smart sampling. There's a potential to understand a graph, the general topology of the graph, with a pretty good understanding that even with like high accuracy of estimation, say 90%, 95%. So most of the case, uh, which can give us a very good guidance even before we run algorithm, so that we know how we can dynamically allocate system resources in the horizontal elastic setup. The fourth and fifth layer of estimation are actually more advanced. So that's basically to estimate like resources that can be allocated sometimes dynamically, but estimate uh, what kind of a model we prefer, centralized versus distributed, and also based on your budget, your system resource, your business priorities, what kind of range of cost you can potentially allocate. Of course, if we are viewing things in a pyramid uh, perspective, the file size of the storage, like the storage engine statistics, of also how you can do pre-statistics, runtime sampling, and even with like user-defined estimation in a heuristic and hinted way. So the graph cost prediction model can be applied into many real world scenarios like financial risk management, risk control, uh, in data governance, and of course in knowledge graph. There are just many areas potentially can use the graph cost prediction model. So let's talk about a little bit about the elastic graph storage. Now, here is let's assume this is the original setup on the left-hand side. In a standalone setup, you have graph data collocated with graph index. And in a very basic, going to a distributed setup, introduce the name server, and you have let's say three more shards, graph data and graph index can still collocate, with each other, but it's now they are partitioned, right? This is a very basic, a way of doing, rudimentary distributed setup. Of course, you can make things a little bit more complex. What's shown here is like you can use standalone plus index, like now, and also index standalone plus data plugin. So graph data and graph index, there are actually four instances here, and graph index topping, graph property index topping, right? So it's clearly more advanced or more sophisticated than than from the previous slide. Now the layout can also be transformed. Remember the first, the very basic setup. The name server potentially contains some graph index, and also graph data are distributed, collocated, and also we can use a really sophisticated. The name server contains the hot, uh, like where the focus is, the attention is, graph index and also caching data, and there are like cold graph index. That's certain level of uh, distribution. Look at the linkage between all of these. This kind of setup can be more sophisticated, right? Also, if we are talking about multiple index coverage, logically speaking, there are like index A and B. How are we gonna divide that simple logic into, for instance, like 9 instances, right? Uh, so essentially, we're talking about layout 1, 0, 1, 2, right? Shard index 0, 1, 2. And break down that. Also, you have A0, A1, AB, A1, A2, and B0, B1, B2. How are you going to partition that into 9 different? There are just many combinations. What's being shown here is just the one possible setup if you want. So the distribution of data is really following principles like sharding principles and also elimination of supernodes. Supernodes can be a quite a major hurdle in highly scalable systems, because once you run into supernodes, things tend to be running just so much slower, right? So Okay, we understand there are the two most prominent sharding principles are edge cut and vertex cut. A different system may prefer different kind of setup. So let's talk about both. For edge cut, it's quite what's illustrated here. It's a quite straightforward, right? It's a each edge is split into two edges, and also we need some kind of hashing mechanism to to glue things together, right? Uh, because the vertices used to be connected and stored in one instance, now potentially are separating into different instances. Uh, so how are you gonna with the introduction of shard, how are you gonna introduce the shard ID together to tag with each source ID and destination ID? So it's actually pretty straightforward here. Nothing that tricky. And also in the vertex cut model, uh, each vertex potentially will be cut into many pieces as you want based on your business logic. But remember the grid setup. In the grid setup, there are a lot of real world application scenarios potentially can be done using vertex cut without losing much or without losing any performance. For instance, like time series data, right? You are doing, assuming you are saving your data 1 month on each uh, HTAP cluster. So that's a typical scenario that all your processings against that single cluster doesn't require the data involvement or migration from other HTAP clusters. So that's one way to make sure that even you do the cut, you do a vertex cut, but it doesn't really affect your performance, right? Now, this is the second case, that elimination of supernode. The tricky part is that this is the logical view, right? Uh, Supernode A connecting with many other uh, vertices. So in the physical storage layout, if we are assigning all the vertices who used to be connected with supernode A, attaching, it's very much like additional attribute or property field to each node, right? And we can eliminate that node, and that node can be just stored once somewhere else, right, in a special layout too, right? That's how we do this kind of elimination of supernode. But of course, uh, in real world applications, you still need to consider that. So going, for instance, like vertex number 3, you can find A, but are you able to go from supernode A to find vertex 3? This basically is the question about, are you going to store these previous edge twice, right? It's a bidirectional storage problem. So we do feel that there are systems, they don't concern, uh, this way traversal. Like if you happen to hit node A, are you able to traverse to node 3, number 3? If you don't care about this, which is fine, right? So this is a perfectly, separating or eliminating the node. But if you are not, if you still need to find, for A3, 3 to A, you need to do things in, in a bidirectional way, then you're gonna still have to figure out you're linking node A to all of these other connecting vertices. You can't just eliminate things once and in a unidirectional way, then losing all the linkages between, from certain directions. Next, let's talk about the step-by-step explain, which is so what I'm going to illustrate that how we do query optimizations. This is not a sophisticated one. So basically what's showing here is like find nodes whose ID equal genius and giving alias as a person. And also we need to, from schema, uh, the company called Ultipa, we need to find that company, right? Out of the nodes, the vertices. And also this is the third clause, is to let's do A to B search, starting from a person, going to a destinations company, which is essentially is the, going from Genius to Ultipa. There are like 7 steps in between, assuming we're searching that deep, and given alias as path and return the path, all the path information, right? The ID, unique ID, the from ID, and to ID. So uh, breaking this declarative text into a logical plan, what we are returning is the path, right? Which is quite straightforward. And also the major operation, the cross instance operation, potentially, cross shard servers operation is the AB path, right? And also there are 2 node searches, right? Uh, we all know the predicate, right? Person, ID, etc., and etc., right? So given the logical plan, we can see that we're going this from right to left, right? We have node search, 2 node search combined to find the AB search, to do the AB path search and return the data, right? If we look at the access method, right? The first node, the first vertex we're trying to find is genius. So we potentially will hit a primary key, right? It's actually called a point query. There are, of course, there are like, range query, primary key, secondary key, point, range. There are many combinations. So the master statistics will be able to suggest what kind of index we're trying to use, to help with our accelerations, right? And the second, we're jumping to the second. The second is a schema based. So the access method is also this is actually, we're using schema here, which is actually comparable, but more, I would say, it's more organized, right? So this is not exactly index, this is schema. And also, so what we have done here is we know that the index search happens with partition 1, and the schema search actually spans across partition 1 too, right? This is like, all of these are done dynamically, right? On the fly. Now here is a full picture before the optimization, like all the possible pathways that potentially will happen to generate, to gather the final return results, right? Index search, schema search, right? Across multiple partitions, and combining the results, do the A/B search and eventually returning, there are actually multiple paths. This is the whole picture. If we are able to breaking things down a little bit, so there are 2 major, I would say, 2 planes, the upper plane and lower plane. So these are the 2 paths that potentially we can go. It's just a matter of which one we shall go, potentially with educated, estimated lower cost. So we're trying to figure out which one has lower cost. Now let's look at this. If we are doing the schema-based node search on partition 2, and combined with the the index node search from partition 1, and eventually the AB is also conducted over partition 1. So there are 2 things to consider. First, read data either you do the read data in advance or in a very lazy mode, right? Delayed mode. And also there is like potential ad scan. You probably should, try to avoid ad scan. Ad scan can be slow. So to summarize that, the optimization techniques potentially can be leveraged are multiple folded, like multiple with the like minimum IO cost model, uh, plus MPP massively parallel processing, and also there there is like dynamic computational path. There are in the in a grid setup, there are vertical, horizontal, and elastic computing graph that can be leveraged. Also, operator assembling, statistical estimation to choose the best execution plans. Of course, this there are arbitrary way of data storage you need to handle. And the other topic is really about how we do distributed transaction from the graph query language perspective. Uh, at the very beginning, the modifications are actually kept in DRAM. And for transaction, for the GQR transaction commit, it's a two-phase. Sometimes people will prefer three-phase. It's up to you. And also, transaction or the event isolation is serializable, right? Now let's go back. Let's revisit uh, in our, practice. We think HTAP distributed consensus setup is still the most cost effective and also can guarantee performance. The key components comparing with the only, the three instance, which can be seen as a extended mode of master slave, but with, just with HTAP capabilities, right? So in this, in larger setup, we are dividing things into multiple, partitioning things into multiple clusters, but we are still maintaining relatively uh, decent performance within each cluster. And the name server is only triggered, uh, when minimum data is aggregated, merged onto the name server. This is a different or optimization, comparing to the traditional name servers functionalities or behaviors, because a lot of the traditional, like all the sharded servers, or they do not have much computing power. But in our setup, in all the HTAP cluster setup, all the servers have adequate computing power, to be able to locally process data. Of course, the limitation here, still I need to point it out, the limitation here is that uh, the partitioning is based on human intelligence. You can't just randomly making the cuts. So that's probably, well, to certain people, that's a disadvantage. Uh, that kind of disadvantage actually can be addressed in a pure, horizontally scalable architecture is illustrated here. We are actually still, actively working on this. Basically, this is a quite sophisticated, scalable graph database system, potentially with unlimited scalability and also with deep data processing and elastic computing capabilities. Uh, all things we talk about up until now. But of course, the sharding here is pretty much done. Even we say this is self-defined sharding. Yes, we are able to support that. But if you prefer, if you want the system to make all the judgment for you, there's a potential you do, automated, fully automated sharding, even without knowing the business logic. But I wouldn't suggest you to do that because sometimes uh, the performance drop may be very significant. Then how you're going to do the optimization. You're going to based on a lot of statistics and estimations to do that, like all things we mentioned in the last couple of slides. uh, but there gotta be use cases that you don't know how much you can go, right? There gotta be use cases. If you randomly if you have everything automated, the performance drop can be uncontrollable. That's my point. That's my point. So you need to be conscious, because logically speaking, a lot of real world scenarios, uh, logically, this is just one potentially within an enterprise. All data can be formed as one gigantic logical graph. But if you really zoom into those data, there are huge potentials to make the cuts, make intelligent cuts. And without knowing the business logics, without knowing, what are the inherent connectivities between those data, and by solely relying on algorithm or the sharding mechanism and expecting that you can just shard freely on the data and still getting super good performance, to us, that's impossible. So to get the best of both worlds, you better apply a lot of human intelligence in for real intelligent sharding, artificial sharding. Don't go fully automated. I think it's gonna we are still a couple years from now before we can realize things can be done fully automated, fully intelligent, and still not losing huge amount of performance by going a partition, things partitioned everywhere. So the two key things we talk about is that low data migration is one key thing, and also compute centric storage, that essentially is the same thing. And also there are a lot of opportunities for for deeper query optimization. The goal are always to achieve better, faster turnaround time. We did some experiment. Well, given the time, we're not able to share too much information here. But basically, I want to summarize that the high density computing is one thing, and also achieving linear scalability is the second thing that we always try to do. But what's unique, what's quite different for the graph database is the ultra deep traversal capabilities, and not to be limited by supernode. That's also a very interesting thing, and without using the high density computing, vector computing, and those techniques, you're not able to penetrate uh, supernodes, uh, let alone ultra deep traversals, like many hops deeper. uh, and we do know that by leveraging HTAP, you can potentially achieve, all the things that you want. With like these are more like the results you can potentially achieve. Lower TCO, time to value, better, much faster time to value, time to market. Of course, usability is another topic. It's just a matter of what kind of toolkits, how easy it is to program to achieve your end goals, your application level goals. Uh, but what we do believe that AI augmentation graph is a perfect tool for for achieving great explainability, acceleration, augmentation, etc., etc. Okay, so I understand we are approaching uh, the end of our presentation. Uh, yeah, still got a couple minutes more. Okay, so I'm going to stop here. Welcome everybody joining this session. We probably got a couple minutes to talk about something else. I'm going to stop here. I probably will be able to take a couple questions if you will. Thank you, everyone. So, guys, if you have any feedback for me for this session, for this conference, feel free just to uh, type in. Okay, cool. All right, thank you. So, guys, take a moment to complete this survey. We appreciate your feedback. Okay, I do see there. Okay, I can see there is one question. Uh, okay, so one. Okay, so Parker asked any performance benchmarks that support the sharding logic, such as LDBC. Uh, so I'm sitting on the board of LDBC. I probably can make a little bit comment about this. Uh, Yes, we are actually working on doing the LDBC benchmark. We are actually well. Let me just give you a quick background. So previously, LDBC has been working on social network benchmarks, and we realized that social network benchmarks are somehow quite different from many real world applications, especially in the financial industries. So we are actually building financial benchmarks. A lot of focus, quite a few companies are working in that direction. Um, we are not able to talk about it, but hopefully by the end of next month, there will be a major ACM conference. LDBC will be sharing more. So I guess by the end of no, it's not actually by June 16th or June 18th, we'll be able to share more information about benchmarks, real world benchmarks, especially around financial benchmarks. Uh, so Matt asked another question. The primary store golden source data stored elsewhere and pull index into the GraphDB for analysis. Okay, so the primary, well, what I'm saying, I guess Matt's question is really about the, the the couple major components we talked about, right? There are storage engine, which is the persistent layer, and also there's a computing engine. I understand where the confusion comes from, because in traditional database we don't talk about compute engine. We only talk about storage, because storage engine handles everything, all the plus indexes. But in graph database, graph query or graph computing engines are a quite unique thing. A lot of people don't realize, because a lot of accelerations are not done entirely on the like the traditional storage engine, meaning on the disks. We have indexes everywhere. I would say that we have both indexes. in-memory data structures, caches everywhere, on disk, in memory. So we're calling this multiple tier storage and computing acceleration techniques. For instance, if you put like not we're not talking about just the acceleration data structure, including not just the B tree, also like Bloom filter, also LSM tree, and also in-memory data structures. For instance, like the skeleton of the graph, all the vertices and their connectivities, uh, and also like data structures when you are doing running graph algorithms, you have that kind of thing, right? You need some kind of in-memory data structure to really help you, running your algorithm. Same for queries, like you are doing traversals, like k-hop, like hopping from certain vertices, for multiple hops. How are you going to do that? How are you going to accelerate that? If you are entirely doing this on disk, even with the help of an index, it's still going to be very, very, very slow. Okay, so I guess we are up for the end of the presentation. I want to thank you, everyone who attend this session. If you have any questions, uh, need any clarifications, I'm very happy to continue the conversation. Maybe over email. Feel free to send me email. You can find me at wiki@ultipa.com. Thank you again. Have a good day.